The coldest place you have ever experienced is not truly cold by cosmic standards. The lowest temperature ever measured on Earth, 89, 2 degrees Celsius at Antarctica's Vostok station, is extreme enough to freeze exposed tissue in seconds and disable machinery. Yet on the absolute temperature scale, it is still about 184 Kelvin, more than 60 times warmer than the average temperature of the universe itself. Beyond Earth's atmosphere lies a cosmos dominated not by heat, but by near-perfect cold. Interstellar space, the vast void between stars, is immersed in the 2.725 Kelvin glow of the cosmic microwave background, the leftover radiation from the Big Bang. Most of the universe exists at temperatures far closer to absolute zero than to any environment humans have ever encountered. This journey explores the physics of cosmic cold, from the outer planets and interstellar space to the coldest known natural locations in the universe, revealing a reality where warmth is the exception and cold is the rule. Why cold in space works nothing like the cold you know. The cold you have experienced in everyday life operates through 3 physical mechanisms, and understanding them is the prerequisite for understanding why the cold of space is categorically different from anything accessible to human sensory experience. Those 3 mechanisms are conduction, convection, and radiation. Each has specific physical requirements, and 2 of the 3 are essentially non-functional in the environment of space. This is the first and most important fact about how cold the universe actually is. The mechanisms that make cold dangerous and perceptible to human beings almost entirely disappear in space, and what replaces them is something far slower, far more patient, and far more absolute in its long-term consequences. Conduction is the transfer of thermal energy through direct physical contact between materials. When you press your palm against a metal surface on a cold morning, heat flows from your warm skin into the cooler metal through the direct collision of molecules at the interface between your skin and the metal surface. The metal atoms, vibrating at lower energy levels than your skin cells, absorb kinetic energy from the faster-moving molecules of your skin and carry that energy away through the bulk of the metal. The rate of conductive heat transfer depends on the temperature difference between the 2 surfaces and on the thermal conductivity of the materials involved, which is why metal feels colder to the touch than wood at the same temperature. Metal conducts heat away from your skin far more efficiently than wood does, draining it faster and producing the sensation of greater cold. Conduction requires physical contact between materials that can transmit molecular kinetic energy. In the interstellar medium, the average density is approximately 1 atom per cubic centimetre. Your bedroom right now contains roughly 27 quintillion molecules of air per cubic centimetre. The interstellar medium contains 1. The best vacuum ever achieved in a terrestrial laboratory still holds billions of atoms per cubic centimetre, orders of magnitude denser than interstellar space. In an environment this empty, conduction as a mechanism of heat loss is essentially non-existent. There are almost no molecules to carry heat away from any surface, and the rare collisions that do occur transfer negligible energy compared to any practical thermal engineering problem. Convection is the transfer of thermal energy through the movement of a fluid, a gas or liquid, carrying heat from one location to another through bulk motion. It is what makes a cold wind feel colder than still air at the same temperature, what makes hot objects cool faster when you blow on them, and what drives the large-scale heat transport systems in Earth's atmosphere and oceans. Convection depends entirely on the existence of a fluid medium through which material can move. In the vacuum of space, there is no such medium. There is no fluid to carry heat away from any object. Convection, like conduction, is effectively non-existent in the interstellar void. What remains is radiation, the emission of electromagnetic energy by any object with a temperature above absolute zero. Thermal radiation is the one mechanism of heat transfer that does not require a material medium and therefore operates in vacuum as effectively as it operates in atmosphere. Every object warmer than absolute zero emits electromagnetic radiation continuously across a spectrum of wavelengths that depends on its temperature. Room temperature objects emit primarily in the infrared. Hotter objects emit increasingly in the visible and then the ultraviolet. The total power radiated per unit area scales with the fourth power of the absolute temperature, meaning that doubling the temperature increases radiated power by a factor of 16. This relationship, described by the Stefan Boltzmann law, governs how objects in space lose their heat. The critical consequence of radiation being the sole heat transfer mechanism in space is that heat loss is dramatically slower than in any environment with a surrounding atmosphere. On Earth, an object losing heat to cold air loses it quickly, through millions of molecular collisions per second, carrying kinetic energy away. In space, the same object loses heat only through the slow, continuous emission of infrared photons radiating outward in all directions. The insulating effect of the vacuum is extraordinary by everyday standards. A thermos bottle achieves its insulating performance by creating a vacuum jacket between its inner and outer walls, eliminating conduction and convection between them. The vacuum of space applies this same principle to every object within it, surrounding each one with the most effective thermal insulation naturally occurring anywhere in the universe. This counterintuitive reality means that the danger of space is not instantaneous freezing, as popular culture often depicts. A human body placed in space would not shatter or freeze solid in seconds. It would actually lose heat relatively slowly compared to what a terrestrial cold environment would produce, because the vacuum is such an effective insulator. The actual immediate threats are the lack of pressure causing dissolved gases to form bubbles in body fluids, the rapid evaporation of moisture from exposed surfaces, and the complete absence of oxygen for respiration. Cold itself, operating purely through radiation in the absence of any conducting or convecting medium, would take hours to reduce a body's temperature to dangerous levels in the absence of sunlight. The cold of space is real, profound, and ultimately absolute in its long-term effects on any object left within it. But it is patient cold, not violent cold, and that distinction matters for understanding what the universe actually is. The baseline temperature of everything, 2.725 Kelvin, and what it means. There is a number that describes the temperature of the universe, not the temperature of any specific object or region within it, but the thermal baseline of the cosmos itself, the temperature of the radiation that fills every cubic centimetre of observable space with equal intensity in every direction. That number is 2.725 Kelvin. It corresponds to minus 270.425 degrees Celsius, or minus 454.765 degrees Fahrenheit. It sits 2.725 degrees above absolute zero, the theoretical minimum temperature at which all thermal motion in matter would cease. To place this in context, the temperature difference between boiling water and freezing water at sea level is 100 Kelvin. The entire range of temperatures in which liquid water exists, the range within which all known life on Earth operates, spans a 100-degree interval on the Kelvin scale. The baseline temperature of the universe sits 2.725 Kelvin above the absolute bottom. Less than 3% of the width of the liquid water temperature range separates the universe's ambient temperature from the theoretical point of zero thermal energy. This temperature is not the temperature of vacuum itself in some abstract sense, because vacuum does not have a temperature in the way that matter does. Temperature is a property of matter, specifically a measure of the average kinetic energy of particles in a substance. What the 2.725 Kelvin number actually describes is the temperature of the cosmic microwave background radiation, the electromagnetic field that fills all of space with photons left over from the early universe. Any object placed in open space, far from any local heat source such as a star, will absorb this background radiation from all directions simultaneously. And if it reaches thermal equilibrium with its radiation environment, it will settle at a temperature of approximately 2.725 Kelvin. This is the temperature the universe imposes on anything that is not being actively heated by some local source of energy. The cosmic microwave background was discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey, who were attempting to use a large horn-shaped antenna originally designed for satellite communications to make precise radio astronomical measurements. They detected a persistent, uniform noise signal arriving from every direction in the sky with equal intensity, indifferent to the time of day or the season. The signal could not be attributed to any local source. It was not from New York City. It was not from the antenna's electronics. It persisted after the two physicists carefully cleaned bird droppings from inside the antenna and verified every component of the system. It was everywhere, always, coming from no particular direction because it came from all directions simultaneously. What they had found, without realizing it initially, was the afterglow of the Big Bang, the thermal radiation left over from the epoch 380,000 years after the universe's origin, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. That radiation has been traveling through space and cooling as the universe expands for 13.8 billion years, stretching from the visible and infrared wavelengths at which it was originally emitted into the microwave regime, where Penzias and Wilson detected it, cooling from approximately 3000 Kelvin at emission to the 2.725 Kelvin measured today. The relationship between the cosmic microwave background temperature and absolute zero tells us something precise and important about where the universe is in its thermal history. Absolute zero, 0 Kelvin, is not merely the coldest achievable temperature. It is the theoretical lower bound on temperature, the state at which particles would have no thermal kinetic energy whatsoever, no random motion, no vibration, nothing but the 0-point quantum mechanical energy that quantum mechanics says can never be entirely removed. The universe has been cooling since its first moment toward this absolute floor. The Big Bang began at temperatures exceeding 10 to the 32 Kelvin, the Planck temperature, above which our current physical theories cannot reliably describe what matter and energy do. The universe has been falling from that inconceivable heat toward absolute zero for 13.8 billion years, and it has covered most of the distance. It sits now at 2.725 Kelvin, within 2.725 degrees of the floor, and it continues to cool as the expansion of space stretches the wavelengths of background photons into longer, lower energy forms. The universe is not going to stop cooling. It will not reach a new equilibrium at 2.725 Kelvin and remain there. It will continue to fall, and the 2.725 Kelvin we measure today represents a snapshot of a universe in motion toward a final cold that has its own name in physics, the heat death, the state of maximum entropy in which no temperature gradient remains and nothing useful can ever happen again. What temperature actually measures and why absolute zero is a wall. Temperature is one of the most familiar physical concepts in everyday experience and one of the most subtly misunderstood at the level that matters for discussing the extremes of the cosmos. Most people have an intuitive sense that temperature measures hotness, that it is a property objects possess to varying degrees, that it flows from hotter things to colder things, and that the direction of this flow is reliable and universal. All of this is correct as far as it goes, but it does not go far enough to explain why absolute zero is fundamentally different from merely a very cold temperature, why it represents not just an extreme on a scale, but a wall beyond which the scale itself ceases to have meaning. Temperature, at the microscopic level, measures the average kinetic energy of the particles composing a substance. In a gas, temperature describes how fast the molecules are moving on average, how energetically they collide with each other and with any surface they encounter. In a liquid, temperature describes the average energy of molecular vibrations and translations within the more constrained geometry of the liquid state. In a solid, Temperature describes the amplitude of atomic vibrations around fixed lattice positions. In all cases, temperature is a statistical description of motion. Hot means fast and energetic. Cold means slow and sluggish. There is nothing arbitrary about this definition. It connects directly to all the macroscopic properties of temperature we observe, including the direction of heat flow, the efficiency of heat engines, and the behaviour of materials across their phase transitions. The implication of this kinetic definition is profound when you trace it to its limit. If temperature measures the average kinetic energy of particles, and if temperature can be reduced by removing energy from those particles, then there must exist a state in which the particles have no kinetic energy attributable to thermal motion, in which they are as slow as they can possibly be. This state is absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. It is not merely the coldest temperature that has been reached, it is the coldest temperature that can exist, because it represents the complete absence of the thermal kinetic energy that temperature measures. There is no temperature below absolute zero, in the same sense that there is no speed greater than the speed of light. Both represent absolute limits set by the structure of physics itself, not by engineering limitations. The qualification that thermal kinetic energy becomes zero at absolute zero matters because quantum mechanics introduces a subtlety. Even at absolute zero, matter retains what is called zero-point energy, a minimum energy that quantum mechanics requires even in the ground state, because the Heisenberg uncertainty principle prohibits a particle from simultaneously having a perfectly defined position and a perfectly defined zero momentum. Particles at absolute zero are therefore not perfectly still in the quantum mechanical sense. They retain this irreducible minimum energy. But this zero-point energy does not register as temperature in the thermodynamic sense because it cannot be extracted or transferred to another system through heat exchange. Temperature, in the precise thermodynamic definition, measures only the energy that is available for exchange, and at absolute zero, none is available. The practical consequence of absolute zero being a theoretical limit rather than an achievable state is that every physical process that involves cooling becomes progressively harder as it approaches absolute zero. This is stated formally in the third law of thermodynamics. It is impossible to reach absolute zero in a finite number of steps. Each step of cooling requires removing some fraction of the remaining thermal energy, and as the remaining energy approaches zero, the difficulty of removing any further fraction increases without bound. The closest any laboratory on Earth has come to absolute zero is approximately 100 billionths of a Kelvin above it, achieved through laser cooling and magnetic trap techniques applied to tiny samples of ultra-cold atoms. These experiments have revealed extraordinary physics that exists only in the regime immediately above absolute zero, including superconductivity, superfluidity, and Bose-Einstein condensation. But the floor itself remains unreached and unreachable. The universe's background temperature of 2.725, Kelvin sits 2.725 Kelvin above this unreachable floor, which sounds close in absolute terms, but represents an enormous richness of thermal activity compared to what sits below it. The difference between 2.725 Kelvin and 0 Kelvin is the difference between a universe with photons, with particles, with the residual motion of atoms exposed to the background radiation field, and a universe in which thermal motion has entirely ceased. Everything in the cosmos, every atom, every molecule, every particle that has ever existed or will ever exist, is warmer than absolute zero. And the universe as a whole is trending toward this wall at an imperceptible but relentless pace. The inner solar system's thermal extremes, a study in contrast. The solar system presents a thermal environment of startling contrasts within a relatively compact volume of space, and tracing those contrasts from the Sun's surface outward to the edge of its influence provides the most vivid available illustration of how dramatically temperature can vary across what is, by cosmic standards, a negligible distance. The Sun at the centre of this system maintains surface temperatures around 5,500 degrees Celsius, nearly 6,000 Kelvin at the photosphere, the visible glowing surface from which sunlight is emitted. This is already a number that exceeds any earthly experience by an enormous factor. The highest temperatures in conventional industrial processes, in steel furnaces and plasma cutters, reach a few thousand degrees. The Sun's visible surface is hotter than any industrial process humans have developed, and it is not even close to the Sun's hottest regions. The solar corona, the diffuse outer atmosphere of the Sun, visible during total solar eclipses as a pearlescent halo of structured plasma extending far beyond the visible disk, reaches temperatures of 1 to several million Kelvin. This is one of the most famous unsolved problems in solar physics. By every expectation of basic thermodynamics, the corona should be cooler than the photosphere below it, because heat flows from hot regions to cool regions and not the reverse. Yet the corona is not slightly warmer than the photosphere. It is hundreds of times hotter. The photosphere is roughly 6,000 Kelvin. The corona is 1 million to 2 million Kelvin or more in some regions. The energy to maintain this temperature against radiative cooling must be coming from somewhere below, transported upward through some mechanism against the direction that naive thermodynamics would predict. The leading candidates involve magnetic energy, specifically the dissipation of energy stored in the Sun's complex magnetic field through reconnection events and wave heating. But the precise mechanism responsible for the corona's extraordinary temperature remains an active area of research with no fully satisfying consensus. Moving outward from the Sun through the inner solar system, the thermal gradient is steep, and the conditions encountered by each planet reflect their specific distances and atmospheric properties in ways that illustrate how temperature is determined by more than just proximity to a heat source. Mercury, the innermost planet, has no significant atmosphere. Without an atmosphere to distribute heat around the planet or to buffer the surface against direct solar radiation, Mercury's sunlit surface reaches approximately 430 degrees Celsius during the long Mercurian day, while the night side plunges to approximately minus 180 degrees Celsius in the darkness. The temperature swing between the two sides of the same planet, across a distance of only 4,880 kilometers, exceeds 600 degrees Celsius. Mercury is not uniformly hot. It is an object of violent thermal contrast made possible by the complete absence of any atmospheric medium to smooth the differences. Venus presents the opposite case. Despite being farther from the Sun than Mercury and receiving less solar radiation per unit area, Venus maintains surface temperatures of approximately 465 degrees Celsius, making it the hottest planetary surface in the solar system. The mechanism is the runaway greenhouse effect produced by Venus's thick carbon dioxide atmosphere, which traps outgoing infrared radiation with such efficiency that the surface temperature has climbed far above what solar heating alone could produce. Venus's surface temperature is remarkably uniform as a result. The day-night contrast is only a few degrees rather than the 600-degree swing on airless Mercury. The greenhouse effect has turned Venus into a thermal pressure cooker, uniform and extreme, where the same temperature that could melt lead persists everywhere on the surface, regardless of the time of day or the latitude. Earth sits at a distance from the Sun, where liquid water is stable over much of the surface, with a global average temperature of approximately 14 degrees Celsius. This comfortable average conceals the range of temperatures actually experienced across the planet's surface, from the Antarctic record of minus 89 degrees Celsius to the Death Valley record of approximately 57 degrees Celsius, a span of nearly 150 degrees within a single planet's surface. The habitability of Earth for life as we know it depends on maintaining conditions within this range, and specifically on keeping liquid water available at the surface, which requires not only the right distance from the Sun, but the right atmospheric composition, the right mass to retain that atmosphere, and the right internal geology to cycle carbon and maintain the greenhouse effect at the appropriate level over geological time. Mars, at roughly 1.5 times Earth's distance from the Sun, receives only about 43% as much solar energy per unit area as Earth does. Its thin carbon dioxide atmosphere provides minimal greenhouse warming and almost no buffering of temperature variations. The result is an average surface temperature of approximately -60 degrees Celsius, with summer daytime temperatures near the equator occasionally reaching +20 degrees and winter nighttime temperatures at the poles falling to -125 degrees Celsius as the thin atmosphere partially freezes out as carbon dioxide frost. Mars is cold not primarily because of its distance from the Sun, but because it has lost the atmospheric thickness needed to retain heat and sustain the conditions that made it, by geological evidence, a warmer and wetter world in its distant past. The outer solar system, where chemistry freezes solid. The transition from the inner solar system to the outer solar system is not merely a change in temperature, it is a change in the nature of matter itself. The substances that constitute the familiar physical world, the water that fills Earth's oceans, the carbon dioxide that makes Venus uninhabitable, the nitrogen that comprises most of Earth's atmosphere, do not merely become colder as you move outward from the Sun. They change phase entirely, from gases and liquids into solids, transforming from the flowing, dynamic materials of the inner solar system into the rigid, frozen ices that define the outer solar system's landscape. Understanding this transformation is not optional for understanding what the outer solar system actually is. It is the central fact about that region of space. Jupiter, the largest planet, has cloud-top temperatures of approximately -145 degrees Celsius. The visible surface of Jupiter that photographs show, the familiar banded structure of orange and white and brown, is not a solid surface at all, but the uppermost layer of an atmosphere so deep and so massive that the pressure at its deepest accessible layers would crush any structure humans have ever built. The cloud-top temperature of -145 degrees is cold enough to freeze water solid, but water in Jupiter's atmosphere exists at this altitude not as liquid or vapor, but as ice crystals forming the bright white ammonia water cloud bands. Deeper in the atmosphere, where pressure and temperature both increase with depth, conditions transition through regimes unlike anything in the inner solar system, ultimately reaching a core that theoretical models place at temperatures of tens of thousands of Kelvin and pressures millions of times Earth's atmospheric pressure at the surface. Saturn's cloud tops reach approximately -178 degrees Celsius, somewhat colder than Jupiter's, and Saturn exhibits the same layered atmospheric structure of ammonia and water ice clouds covering a deep hydrogen-helium interior. What makes Saturn thermally distinctive is its low density, the lowest of any planet in the solar system, lower even than liquid water, and its internal heat source. Saturn radiates approximately 2.5 times more energy into space than it receives from the Sun. This excess energy comes from its interior, specifically from a process called helium rain, in which helium droplets condense in Saturn's hydrogen atmosphere at depth and sink toward the core, releasing gravitational potential energy as heat. The Saturn we observe is still warm from its formation and from this ongoing differentiation process in ways that its temperature alone does not fully reveal. Uranus sits at approximately 19.8 times Earth's distance from the Sun and receives roughly 0.27% of the solar energy that falls on Earth per unit area. Its cloud tops are approximately -224 degrees Celsius, making its atmosphere the coldest in the solar system among the major planets. Uranus is thermally anomalous in a different way from Saturn. Unlike every other giant planet, Uranus emits almost no more energy than it receives from the Sun. It has essentially no detectable internal heat source, which means that whatever primordial heat it stored at formation has either already been lost or is trapped in its interior by some structural barrier that prevents it from reaching the surface. The leading theory for this anomaly is that a large impact early in the solar system's history tipped Uranus onto its side and simultaneously disrupted its internal structure in a way that created a stable stratification, preventing deep convection. The result is a planet that is cold throughout in a way that its siblings are not. Neptune, the most distant major planet, has cloud-top temperatures of approximately -214 degrees Celsius, somewhat warmer than Uranus, despite being farther from the Sun. Because unlike Uranus, Neptune does retain a significant internal heat source, radiating roughly 2.6 times the energy it receives from the Sun. Its moon, Triton, orbiting in the retrograde direction that marks it as a captured Kuiper Belt object, rather than a body that formed in place, has surface temperatures of approximately -235 degrees Celsius, approaching the temperature of liquid nitrogen. Triton's surface of nitrogen ice is so cold that sunlight, even at Neptune's distance, is energetically significant relative to the thermal energy of the surface, and the tiny flux of solar energy that reaches Triton is sufficient to drive active nitrogen geysers, sublimating ice from beneath the transparent nitrogen frost and launching dark plumes kilometers into the thin atmosphere. At -235 degrees, the threshold between solid and sublimated nitrogen is so close to the ambient temperature that the smallest energy input from the Sun is sufficient to trigger geological activity. Pluto, orbiting in the Kuiper Belt at an average distance of roughly 39.5 times Earth's distance from the Sun, has surface temperatures between approximately -218 and -240 degrees Celsius, depending on location and time. The New Horizons flyby in July 2015 revealed a world of extraordinary geological complexity for something this cold. Mountains of water ice standing kilometers high, vast plains of nitrogen ice smooth enough to suggest recent geological activity, a layered atmosphere of nitrogen and methane haze extending hundreds of kilometers above the surface. Pluto's geology is driven by the phase behavior of its surface ices, nitrogen and methane, and carbon dioxide cycling between solid and vapor phases, as Pluto's highly eccentric orbit brings it closer to and farther from the Sun over its 248-year orbital period. At these temperatures, nitrogen and methane are not the atmospheric gases familiar from Earth's environment. They are the surface materials, the ice that covers the ground, the rock of which the landscape is made, and they flow with the dynamics of a geologically active world, despite temperatures that would freeze the atmosphere of any inner system planet solid in minutes. The heliopause and what lies beyond, the true cold of interstellar space. The solar system does not end at the orbit of Neptune or Pluto. It extends outward through a vast, largely unmapped region of icy debris in the Kuiper Belt, and beyond that, into the theoretical Oort cloud, a spherical shell of cometary bodies that may extend to distances of tens of thousands of astronomical units from the Sun, perhaps a third of the way to the nearest star. But the boundary that most clearly marks the transition from the Sun's domain to interstellar space is not defined by any particular object. It is defined by a pressure balance, the point where the outward flow of the solar wind, the continuous stream of charged particles emitted by the Sun in all directions, exactly balances the pressure of the surrounding interstellar medium. This boundary is called the heliopause, and crossing it means leaving the Sun's protective bubble entirely and entering the interstellar medium proper. Voyager 1 crossed this boundary in August 2012 at a distance of approximately 121 astronomical units from the Sun, and Voyager 2 crossed it in November 2018 at approximately 119 astronomical units in a different direction. These crossings were the first time any human-made objects had entered the true interstellar medium, and the measurements transmitted back from both probes across communication delays of over 17 hours have revealed an environment substantially different from what theorists had predicted. The magnetic field beyond the heliopause has a different orientation and structure than the solar wind's magnetic field within. The plasma density increases sharply at the crossing. The flux of low-energy cosmic rays, partially excluded from the interior of the heliosphere by the solar wind's magnetic field, increases significantly beyond the boundary. The interstellar medium is not the simple, uniform environment that simple models had depicted. The temperature of the interstellar medium is one of the more counterintuitive facts in space science. The kinetic temperature of the sparse particles in the local interstellar medium, the measure of how fast those individual particles are moving, is actually relatively high, on the order of thousands to tens of thousands of Kelvin in some measurements. This does not mean the interstellar medium is warm in any practical sense. It is not. The kinetic temperature of particles is only a useful measure of thermal energy in systems dense enough that particles are actually exchanging energy through frequent collisions. In a medium containing 1 atom per cubic centimetre, individual particles can have high velocities without there being any meaningful heat available for transfer, because they almost never collide with anything. An object placed in the interstellar medium would not be heated to thousands of Kelvin by the sparse energetic particles around it. It would reach thermal equilibrium with the radiation field it is bathed in, which is the cosmic microwave background at 2.725 Kelvin, absorbing and re-emitting the background photons until it settles at that temperature. The radiation temperature and the kinetic temperature of the sparse particles are decoupled in a way that has no analogue in any dense material environment. What Voyager 1 and Voyager 2 have measured beyond the heliopause is an environment where the Sun's influence has essentially ceased. No solar wind plasma, no solar magnetic field. Cosmic rays arriving freely from the galaxy in all directions, rather than being partially excluded by the heliospheric field. The spacecraft continue to return data, though with diminishing power as their radioisotope generators decay, and the data they send back is the only direct measurement of the local interstellar medium from any human-made instrument. Their trajectories will carry them into the Oort cloud in roughly 300 years, where they will be unable to detect any of the icy bodies around them, as their instruments will have long since fallen silent, and out through the far side of the Oort cloud in tens of thousands of years, entering the interstellar medium fully and finally for the indefinite future. By then they will be cold, dark, inert, their internal heat sources exhausted, equilibrated to the 2.725 Kelvin of the cosmic background radiation, indistinguishable from the temperature of the universe around them. The coldest natural places in the universe and what produces them. The cosmic microwave background at 2.725. Kelvin is the average temperature of the universe, but it is not the coldest. There exist places in the cosmos that are colder than the ambient background radiation. Places where physical processes have actively driven temperatures below the baseline that fills all of space. These locations are scientifically extraordinary, not because they are merely extreme, but because they reveal specific physical mechanisms that can produce cold beyond what the universe provides as a default, and because they are the environments where some of the most unusual and important chemistry and physics in the cosmos occurs. The Boomerang Nebula, located approximately 5,000 light-years from Earth in the southern constellation Centaurus, holds the record for the coldest confirmed natural environment in the observable universe. Its temperature has been measured at approximately 1 Kelvin, 1 degree above absolute zero, and roughly 1.7 Kelvin colder than the surrounding cosmic microwave background. The mechanism producing this extraordinary cold is not exotic physics, but a straightforward thermodynamic process operating at enormous scale, adiabatic cooling through rapid gas expansion. The Boomerang Nebula is a young planetary nebula. the expanding shell of gas ejected by a dying star in the late stages of its evolution. The gas in the nebula is expanding outward from the central stellar remnant at approximately 164 kilometers per second, far faster than typical planetary nebulae, and this rapid expansion causes the gas to cool through the same principle that makes aerosol sprays feel cold when they expand out of their containers, or that causes air to cool as it expands through a refrigerator's expansion valve. Work is done by the expanding gas against the pressure of the surrounding environment, and this work comes at the expense of the gas's internal thermal energy. The result is a rapid temperature drop that has carried portions of the Boomerang Nebula below even the temperature of the cosmic background that fills the surrounding space. Dense molecular clouds, the enormous assemblages of gas and dust from which new stars and planetary systems form, contain cold interior regions where temperatures approach 10 Kelvin, or even lower in some cases. These clouds are cold primarily because they are dense enough to shield their interiors from the heating effects of nearby stars' ultraviolet radiation and from the cosmic microwave background's photons, which cannot penetrate deeply into the dense gas. The cold interiors of molecular clouds are also the sites of the most complex abiotic chemistry known in space, a topic explored in more depth in a later chapter. They are the regions where the gravitational collapse that eventually produces new stars begins, and the specific temperatures within them, between 10 and 30 Kelvin in most cases, set the initial conditions for the structure of the clouds as they collapse. The void regions of the cosmic web, the enormous nearly empty bubbles that occupy most of the volume of the observable universe between the filaments and clusters where galaxies reside, are colder than the average background. Because voids contain essentially no stars, no galaxies, no sources of local heating, the gas within them is cooled by the expansion of the universe and heated by very little else. Recent measurements using the thermal Sunyaev-Zeldovich effect have allowed estimates of the gas temperature in cosmic voids, finding values slightly below the average cosmic background temperature due to the relative rarefaction of even the background radiation in these underdense regions. The voids are the most extensive cold environments in the universe by volume, constituting perhaps 80% of the universe's total volume, and they are approaching the background temperature from both above and below as the universe expands and the temperature gradient between denser and less dense regions smooths out. Below these natural cold environments, in the domain of laboratory physics rather than astrophysics, human technology has achieved temperatures dramatically lower than anything the natural universe produces. The coldest temperatures ever achieved are in laboratory experiments using laser cooling and magnetic trap techniques on collections of atoms cooled to within a few nanokelvins or even picokelvins of absolute zero. At these temperatures, matter exhibits quantum mechanical behaviors that have no classical analog, including the formation of Bose-Einstein condensates, in which bosonic atoms lose their individual identities and merge into a single quantum state, and the observation of superfluidity in dilute atomic gases. These laboratory temperatures are far colder than anything in nature, yet they remain above absolute zero because the third law of thermodynamics forbids achieving the floor itself. The universe has never been colder than about 2.725 Kelvin in the current epoch outside of laboratory conditions, and the natural mechanisms that produce temperatures below this value are limited to the specific physical processes described above. Adiabatic expansion in certain expanding nebulae, and the shielding effects that allow molecular cloud interiors to drop below the average radiation field temperature. What extreme cold does to matter, from brittle metal to quantum fluids. Temperature is not merely a number that describes how energetic particles are. It is a physical condition that determines what matter fundamentally is, how it is structured, what properties it possesses, and what it can do. The transition from warm to cold is not simply a change in degree, but in many cases a change in kind, a transformation of materials from one state of existence to another that is governed by phase transitions as fundamental as the more familiar transitions between solid, liquid, and gas. Understanding what extreme cold does to matter is essential for understanding both the engineering challenges of spacecraft that must operate in the outer solar system and the scientific significance of the very cold environments in space where exotic states of matter exist and novel chemistry becomes possible. The most immediately practical transformation that cold produces in common materials is the ductile to brittle transition in metals. At temperatures found in moderate Earth climates, most structural metals, including steel, are ductile. They can be bent, stretched, deformed under stress, and they fail gradually with warning signs of deformation before final fracture. The atoms in the metal's crystal lattice can rearrange themselves slightly under stress, allowing the material to deform plastically rather than fracturing catastrophically. As temperature drops, the thermal vibrations of the atoms that give them this mobility diminish. Below a characteristic temperature specific to each metal and alloy, the lattice atoms lose the thermal energy needed to rearrange under stress, and the material transitions to brittle behavior. It fractures suddenly under loads that would merely deform it at higher temperatures, without the progressive deformation that provides warning of imminent failure. This transition is not a minor engineering concern. It has caused catastrophic failures in real engineering systems. Steel used in the hull of the Titanic, analysed from samples recovered from the wreck site, was found to contain elevated sulfur content and to have particularly poor low-temperature toughness. Tests on the recovered steel show that at the temperature of the North Atlantic on the night of April 14, 1912, approximately -2 degrees Celsius, the material was near or within its ductile to brittle transition range. When the ship struck the iceberg, the steel did not dent and crumple in the way the tougher, more ductile steel would have done. It fractured along seams, opening gaps that allowed seawater to flood far more rapidly than a deformed but intact hull would have permitted. The temperature of the ocean did not cause the collision, but it changed the nature of the material that failed, and the nature of that failure determined the pace of the flooding and ultimately the number of people who died. Cold changed what the metal was, and the change was catastrophic. At the temperatures of liquid nitrogen, approximately -196 degrees Celsius or 77 Kelvin, this brittleness is extreme. Materials that are ductile and tough at room temperature become fragile and shattering. Rubber, which at room temperature is flexible and elastic, becomes rigid and brittle enough to shatter under impact. Plastics that flex and bend at normal temperatures crack under stress at liquid nitrogen temperatures. The mechanical properties of materials cannot be assumed to remain constant across the temperature ranges encountered in space missions to the outer solar system, and every material used in a spacecraft destined for cold environments must be tested at the temperatures it will actually experience, not merely at Earth surface laboratory conditions. Beyond the ductile to brittle transition, cold produces genuinely exotic transformations in matter that have no analogue in everyday experience. Liquid helium cooled below 4.2 Kelvin at atmospheric pressure becomes a normal liquid. Cooled further to 2.17 Kelvin, it undergoes a phase transition to a superfluid state in which viscosity vanishes completely. A superfluid has zero internal friction. It can flow through impossibly narrow channels without any resistance. It will climb the walls of its container under the influence of its own surface tension and flow over the rim, driven by the quantum mechanical requirement to minimize its energy. It can sustain persistent flow in a ring indefinitely once established, without any driving force, because there is no friction to slow it down. These behaviours are not merely strange laboratory curiosities. They reflect the quantum mechanical nature of matter at temperatures so low that thermal fluctuations can no longer mask the wave-like properties of atoms, and the atoms of helium-4 condense into a collective quantum state that has no classical description. Superconductivity, the complete disappearance of electrical resistance in certain materials below a critical temperature, is similarly a manifestation of quantum mechanics made accessible by extreme cold. In a normal metal, electrons moving through the lattice of ions experience resistance from collisions with lattice vibrations and impurities. These collisions dissipate energy as heat and limit the electrical current. Below the critical temperature for a superconducting material, electrons form pairs called Cooper pairs that move through the lattice without scattering, carrying current with zero resistance indefinitely. Superconductors expel magnetic fields from their interiors in what is called the Meissner effect, allowing them to levitate above permanent magnets in demonstrations that seem to violate intuition. The applications of superconductivity in magnetic resonance imaging, in particle accelerators, in proposed maglev transportation systems, all depend on the quantum mechanical transformation of matter that cold alone makes possible. Cold chemistry: how the universe builds complexity at near absolute zero. The intuition that chemistry stops in the cold is correct in one important sense and profoundly wrong in another. Warm chemistry, the chemistry of life, of metabolism, of industrial synthesis, of combustion and corrosion, and the reactions that transform materials in everyday experience, does indeed slow and eventually stop as temperature drops. Every chemical reaction has an activation energy, a thermal barrier that reactants must overcome to convert into products. And as temperature drops, the fraction of molecular collisions energetic enough to surmount this barrier decreases exponentially. Cold is, in this sense, an inhibitor of the chemistry that warm worlds are built on. The metabolism of living organisms stops when body temperature drops far enough. The chemistry of the upper atmosphere slows at night when it cools slightly. Industrial processes must be heated to drive reactions that would proceed too slowly at room temperature. The pattern is consistent and the trend is clear: cold slows chemistry. But in the extreme cold of interstellar molecular clouds, at temperatures between 10 and 30 Kelvin, something different happens that defies this simple expectation. Chemistry does not stop. It does not merely slow to imperceptible rates. Instead, it shifts to a qualitatively different regime, governed not by thermal collision energies, but by quantum mechanical tunneling, a process by which particles can penetrate through energy barriers that classical physics would forbid them from crossing at all. Quantum tunneling is not a warm temperature phenomenon that disappears as temperatures drop. It is inherently quantum mechanical and becomes relatively more important at low temperatures precisely because thermal excitation over barriers becomes less important. At sufficiently low temperatures, tunneling is the dominant mechanism by which certain reactions proceed, and these reactions can be specifically the ones that build molecular complexity in ways that would be impossible through thermal chemistry alone. The observational evidence for complex chemistry in cold molecular clouds is extensive and continuously growing. Radio astronomers using millimeter and submillimeter wavelength telescopes have identified hundreds of distinct molecular species in interstellar molecular clouds by detecting the characteristic rotational spectral lines that each molecule emits. These molecules include species of remarkable complexity: methanol, ethanol, formic acid, glycolaldehyde, which is a simple sugar molecule, acetaldehyde, dimethyl ether, methyl formate, ethylene glycol. Some of these molecules have carbon chains of 5 or 6 atoms. Some are directly relevant to biochemistry as we know it on Earth. Glycolaldehyde is a sugar that reacts with glyceraldehyde to form ribose, one of the sugars in RNA. These are not the simple 2 and 3 atom molecules that warm chemistry would naturally produce first. They are the products of a chemistry that has been running in the cold dark of molecular clouds for millions of years, building complexity through processes that do not require warmth. The formation mechanism for most of these complex molecules involves grain surface chemistry, the accumulation of simple molecules onto the surfaces of tiny dust grains, followed by reactions between these adsorbed species that are facilitated by tunneling, by ultraviolet photolysis in the outer regions of clouds where starlight can penetrate, and by cosmic ray ionization of molecules in the shielded interiors where ultraviolet cannot reach. A dust grain in a molecular cloud accumulates ice mantles of water, carbon monoxide, carbon dioxide, methanol, and ammonia over millions of years, one molecule at a time. On these ice surfaces, reactions can occur between species that would never encounter each other in the gas phase due to the extreme diluteness of the medium. The grain surface acts as a concentrator and a reaction substrate, bringing molecules together and keeping them in proximity long enough for reactions to occur. The tunneling of hydrogen atoms, which are light enough to tunnel through energy barriers efficiently even at 10 Kelvin, is particularly important in building up larger molecules through sequential hydrogenation reactions that add hydrogen atoms to carbon and oxygen backbones. The molecules synthesized in molecular clouds are not merely chemical curiosities. They are incorporated into the material from which new stars and planetary systems form when a molecular cloud collapses under gravity. The solar system formed from a molecular cloud, and the material that did not fall into the sun was incorporated into the planets, moons, comets, and asteroids. Comets in particular, having spent most of their existence in the cold outer solar system far from the sun's destructive radiation, preserve a chemical record of the molecular cloud material from which the solar system formed. The Rosetta mission's observations of Comet 67P/Churyumov-Gerasimenko detected glycine in the comet's outgassing material, an amino acid, one of the 20 standard building blocks of proteins in every living organism on Earth. Glycine in a comet, formed in all likelihood through quantum chemistry on coal-grained surfaces in the molecular cloud that preceded the solar system, preserved in frozen ice for 4.5 billion years. Detected when the comet approached the Sun close enough to begin sublimating its outer layers and releasing what had been locked inside since before Earth formed. The cold of interstellar space is therefore not merely the thermal baseline of the cosmos. It is an active chemical environment. It is where the building blocks of life were assembled before the solar system existed, in the cold between stars, through quantum chemistry on dust-grained surfaces over timescales of millions of years. The warmth of stars is what makes planets habitable, but the cold between the stars is where the molecular foundation of habitability was built. Both are necessary. The cold is not the enemy of life's possibility. It is part of the process by which life's chemical ingredients are produced and preserved. The heat death and why cold is the universe's final destination. The second law of thermodynamics makes a statement about the universe that is among the most profound and most unsettling in all of science. Entropy, the measure of disorder and the diffusion of energy into its most probable configurations, always increases in an isolated system. The universe, taken as a whole, is the largest isolated system available for consideration, and the second law applies to it without exception or escape. Entropy increases. Energy spreads from concentrated useful forms into diffuse equilibrated forms from which nothing useful can be extracted. Temperature gradients, the differences between hot and cold regions that make all energy conversion possible, always tend to flatten. Heat always flows from hot to cold and never spontaneously the reverse. These are not tendencies or preferences. They are laws, the most reliably confirmed laws in the history of physics, obeyed without exception in every system ever studied. The consequences of the second law applied to the universe as a whole over cosmological timescales lead to what physicists call the heat death, a term that describes not a dramatic catastrophic event, but a state of final equilibrium. The heat death is the condition in which the universe has reached maximum entropy. All available energy has been distributed as uniformly as possible among all the degrees of freedom available to it. All temperature gradients have been eliminated, and no process capable of doing useful work, converting energy from one form to another, can occur anywhere. In the heat death, the universe is not hot, it is the opposite. It is cold and uniform, a vast, dark, featureless expanse at a temperature indistinguishable from absolute zero, where nothing happens because there is no gradient to drive anything to happen. The current universe is far from this state. We live in what is, cosmologically speaking, an extraordinarily early and energetically rich period of cosmic history. Stars are still forming from collapsing molecular clouds. Galaxies are still active with stellar evolution, supernova explosions, the synthesis of heavy elements in stellar interiors and their dispersal into the interstellar medium, where they can become the raw materials of new planetary systems. Black holes at the centers of galaxies are still accreting material and converting gravitational energy into radiation. The cosmic microwave background, the residue of the Big Bang, is still 2.725 Kelvin, far above absolute zero, still carrying energy that can in principle do work against the absolute zero background. The universe is thermodynamically alive in ways that will not persist. The sequence by which the universe approaches its final cold state unfolds on timescales that make the current age of the universe seem negligible. The Sun will exhaust its hydrogen fuel in approximately 5 billion years, expanding through a red giant phase and eventually settling as a white dwarf, a cooling remnant that will radiate its stored thermal energy into space over trillions of years as it cools toward the ambient temperature of whatever the cosmic background has reached by then. The last stars to form, tiny red dwarfs burning their hydrogen fuel so slowly they can sustain fusion for trillions of years, will eventually exhaust their fuel as well. Models suggest the last stellar light will fade in approximately 100 trillion years, roughly 10,000 times the current age of the universe. After that, a dark era of black holes and cold stellar remnants. The black holes that survive from the era of stellar and galactic activity will then dominate the universe's mass energy for an unimaginably longer period. Black holes are not static. They radiate through the quantum mechanical process of Hawking radiation, emitting thermal radiation at a temperature inversely proportional to their mass. A solar mass black hole has a Hawking temperature of approximately 60 nanokelvins, far colder than the current cosmic background and negligible compared to any relevant thermal energy scale. But as the cosmic background temperature continues to fall with the expansion of the universe, eventually it will drop below even the Hawking temperature of stellar mass black holes, at which point those black holes will begin to lose mass more rapidly than they gain it from the background. They will evaporate. The evaporation of a solar mass black hole takes approximately 2 times 10 to the power of 67 years. Supermassive black holes containing billions of solar masses take correspondingly longer, up to perhaps 10 to the power of 100 years for the largest. After the last black hole has evaporated, the universe is left with only the most diffuse possible radiation field, scattered elementary particles, and the quantum mechanical zero-point energy of the vacuum, cooling asymptotically toward a temperature that approaches but never quite reaches absolute zero. The heat death is not a death in any dramatic sense. It is a silence, a stillness, an equilibration. It is the universe having finished the work of distributing its energy as uniformly as physical law permits. And the temperature at which this final state exists is as close to absolute zero as thermodynamics allows, effectively cold beyond any current experience. Cold in a way that makes the 2.725 Kelvin of today's cosmic background seem warm by comparison, cold without any local exception, without any warm island in the void, without any gradient that could drive any process anywhere. The universe began in fire and will end in cold. The cold of space, the baseline condition we have been exploring throughout this script, is not a temporary condition or an unusual one. It is the universe's default and its destiny. We exist in the brief, improbable, thermally exceptional period between these two extremes, warmed by a star that will not last forever, in a universe that has been cooling since its first moment, and will continue to cool until nothing remains but the cold itself. How spacecraft survived the cold, engineering against the void. The challenge of keeping a spacecraft functional in the thermal environment of space is not the challenge of preventing it from freezing solid in seconds. As established in Part 1, the vacuum of space is an extraordinarily effective thermal insulator, and objects within it lose heat only through radiation, a process that is slow and manageable by engineering standards. The actual thermal engineering challenge of spaceflight is more nuanced and in many respects more demanding than simple protection against cold. It is the challenge of managing the simultaneous extremes of intense solar heating on sunlit surfaces and deep radiative cooling on shadowed surfaces, maintaining a stable internal temperature environment for sensitive electronics and instruments that have narrow operational ranges, and doing all of this with limited power and mass across missions lasting years or decades. The International Space Station illustrates this challenge at its most immediate and most dramatic. In low Earth orbit, the station completes approximately 16 orbits per day, cycling between full sunlight and Earth's shadow roughly 8 times per 24 hours. On the sunlit side, solar flux heats expose surfaces to temperatures approaching 120 degrees Celsius. On the shadowed side, the same surfaces cool through radiation toward temperatures as low as -157 degrees Celsius. The station's external surfaces experience a temperature swing of nearly 280 degrees Celsius every 45 minutes as they transition from sunlight to shadow and back again. No simple passive insulation can accommodate this range. The station's thermal control system uses a closed-loop ammonia cooling circuit that circulates coolant through heat exchangers inside the pressurized modules, collecting waste heat from electronics and crew metabolic output, and delivering that heat to external radiator panels where it is radiated into space. The system is actively controlled by computers monitoring temperatures throughout the station, adjusting flow rates and radiator orientations to maintain internal temperatures between 18 and 26 degrees Celsius, regardless of the external thermal environment. For missions to the outer solar system, the engineering challenge shifts from managing excess solar heat to maintaining adequate warmth in an environment where solar flux is negligible. At Jupiter's distance, solar intensity is roughly 4% of what Earth receives. At Saturn, it is 1%. At Pluto, it is 0.07%. Solar panels become impractical as the primary power source beyond approximately 5 astronomical units, and radioisotope thermoelectric generators become the only viable power source for long-duration missions. These devices, which convert the heat of decaying plutonium-238 into electricity through thermoelectric junctions, provide both electrical power and a steady thermal output that serves the secondary function of keeping the spacecraft warm. The Voyager probes, launched in 1977 and now in interstellar space, continue to function in part because their RTGs produce enough waste heat to maintain critical electronics above their minimum operating temperatures, even as that heat output declines by approximately 4 watts per year as the plutonium decays. The thermal design of any mission to the outer solar system must account for the progressive decline of RTG output over the mission's lifetime and plan for which systems must be kept warm as power budgets tighten. Heaters are used to maintain propellant lines, attitude control electronics, and science instruments above their operational minimums. But as RTG output decreases, heaters must be selectively deactivated, allowing some components to cool below their operational range in order to maintain others. The mission team must decide which capabilities to sacrifice to preserve the most scientifically valuable remaining systems. And these decisions become increasingly constrained as the mission ages. Voyager 1's science team has been managing exactly this declining budget since the 1980s, shutting down instruments one by one to conserve power for the few remaining that can still return unique scientific data from their position in the interstellar medium. Multi-layer insulation blankets, made from dozens of alternating layers of aluminized mylar or Kapton film, separated by thin mesh spaces, wrap most of the critical thermal mass of any deep space spacecraft. Each reflective layer bounces back a fraction of the infrared radiation that would otherwise pass through, and the cumulative effect of many layers reduces thermal emission to a small fraction of what an uninsulated surface would produce. The engineering of these blankets balances their insulating efficiency against their mass, since every kilogram of insulation is a kilogram not available for scientific payload, and their manufacturing quality, since any gap or fold in the layered structure creates a thermal short circuit that undermines the insulating performance of the surrounding blanket. The James Webb Space Telescope represents the most sophisticated passive thermal management system ever deployed in space. Its 5-layer sunshield, each layer illuminized to reflect sunlight, separates the telescope from the Sun, Earth and Moon simultaneously by placing the telescope at the Earth-Sun L2 Lagrange point, where all 3 heat sources are in the same general direction. The temperature on the sun-facing side of the innermost shield layer reaches approximately 110 degrees Celsius. On the telescope side of the outermost layer, the temperature is approximately -233 degrees Celsius. Each successive layer of the shield intercepts a fraction of the radiation that passes through the previous layer, and by the 5th layer, the transmitted solar heat has been reduced to a level that allows the telescope optics and near-infrared instruments to cool passively to approximately -233 degrees Celsius, without any active refrigeration. Only the mid-infrared instrument, which requires temperatures below -266 degrees Celsius to achieve the sensitivity needed for its science objectives, requires active cooling from a mechanical cryocooler. The elegance of this design, achieving temperatures colder than liquid nitrogen in space using only passive thermal management, reflects decades of engineering development applied to the specific challenge of making cold work for astronomy. The Casimir effect and the energy of empty space. The vacuum of space, cold as it is not empty in the way that the intuitive concept of emptiness implies. Quantum field theory, the framework that describes matter and energy at the most fundamental level accessible to current physics, makes a specific and testable prediction about the nature of the vacuum. It is not a featureless void, but a dynamic quantum system in which fields fluctuate continuously, even in the complete absence of particles. These fluctuations, called vacuum fluctuations or zero-point fluctuations, are not a residue of particles that have passed through or an artifact of measurement. They are a genuine property of the quantum vacuum itself, required by the mathematical structure of quantum mechanics, specifically by the uncertainty principle, which prohibits any physical quantity from simultaneously having a perfectly defined value and a perfectly defined rate of change. The electromagnetic field, which describes both light and the interactions between charged particles, fluctuates in this way even in perfect vacuum. Virtual photons, excitations of the electromagnetic field that exist transiently without violating energy conservation within the window permitted by the uncertainty principle, are continuously created and annihilated throughout all of space. These virtual photons are not directly observable as individual particles, but their collective effect on observable quantities is real and measurable. The most famous demonstration of this is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and first measured experimentally by Stephen Lamoureux in 1997. Casimir's prediction was elegant and specific. If 2 uncharged, perfectly conducting metal plates are placed very close together in a vacuum, the virtual photon spectrum between the plates is constrained by the boundary conditions imposed by the plates themselves. Wavelengths longer than the gap between the plates cannot fit between them. The electromagnetic vacuum between the plates is therefore depleted of long wavelength virtual photon modes that are freely present outside the plates. The energy density of the vacuum between the plates is therefore slightly lower than the energy density outside. because those long wavelength modes are absent. This difference in energy density produces a real physical force, pushing the plates toward each other, attempting to reduce the gap and thereby lower the total vacuum energy of the system. The force is tiny for macroscopic plates at ordinary separations, equivalent to a small fraction of a gram of weight at separations of a micron. But it is measurable, and Lamoureux's measurement confirmed Casimir's prediction to within 5%, a result subsequently refined to within 1% by later experiments. The Casimir effect has practical consequences in nanotechnology and microelectromechanical systems, where components separated by gaps of nanometers to micrometers experience Casimir forces strong enough to cause unexpected stiction, surfaces sticking together when they approach too closely, and the Casimir attraction becomes comparable to restoring forces. Engineers designing nanoscale devices must account for Casimir forces as a real and significant effect, not a theoretical curiosity. Proposals have been made for using Casimir forces constructively in nanoscale machines, exploiting the geometry dependence of the effect to engineer specific force profiles. The deeper significance of the Casimir effect for understanding the cold of space is what it reveals about the nature of the quantum vacuum. The cold emptiness of interstellar space is not the simple absence of anything. It is a dynamic quantum system seething with virtual fluctuations that carry real energy and produce real forces. The universe at its coldest and most seemingly empty is not passive or inert. It is active at the quantum level in ways that have measurable consequences. The question of how this vacuum energy is connected to the large-scale structure and dynamics of the universe is one of the deepest unsolved problems in physics. The observed accelerating expansion of the universe, driven by what is called dark energy, has a magnitude that corresponds to a specific energy density of empty space. The quantum vacuum should contribute to this energy density, and Casimir effect measurements confirm that vacuum energy is real and non-zero. But when theorists calculate the expected contribution of vacuum fluctuations to the cosmological constant, the parameter that describes the energy density of empty space in Einstein's equations of general relativity, they obtain a number roughly 10 to the power of 120 times larger than the observed value of dark energy. This discrepancy, sometimes described as the worst prediction in the history of theoretical physics, indicates that something in the relationship between quantum mechanics and gravity is deeply misunderstood. The energy of the cold vacuum of space points to a fundamental gap in current physical theory at the intersection of quantum mechanics and cosmology, a gap that remains open and that represents one of the central challenges of theoretical physics in the 21st century. Hawking radiation and the temperature of black holes. Black holes are among the most extreme objects in the universe, regions where the curvature of space-time becomes so severe that nothing, not matter, not light, can escape once it has crossed the event horizon. For most of the history of physics, black holes were treated as thermodynamically perfect absorbers. Objects that took in everything and gave back nothing, with a temperature of absolute zero in the sense that they emitted no thermal radiation whatsoever. This understanding was overturned in 1974 by a calculation that stands as one of the most surprising and influential results in the history of theoretical physics, performed by Stephen Hawking using a combination of quantum field theory and general relativity that had never been applied in quite this way before. Hawking's calculation showed that black holes are not perfectly cold. They emit thermal radiation, now called Hawking radiation, through a quantum mechanical process that occurs near the event horizon. The mechanism involves the quantum vacuum fluctuations described in the previous chapter. Virtual particle-antiparticle pairs are continuously being created and annihilated throughout all of space, including near the event horizon of a black hole. Ordinarily, these pairs exist for only the brief interval permitted by the uncertainty principle before annihilating and returning their borrowed energy to the vacuum. But near an event horizon, One member of a pair can fall inside the horizon while the other escapes. The infalling particle carries negative energy into the black hole, reducing its mass slightly, while the escaping particle carries positive energy away from the black hole as real radiation. The result is that the black hole slowly loses mass while emitting a thermal spectrum of radiation that corresponds to a specific temperature. The temperature of Hawking radiation depends on the mass of the black hole in an inverse relationship. Larger black holes are colder, and smaller black holes are hotter. For a black hole with the mass of the Sun, the Hawking temperature is approximately 60 nanokelvins, 60 billionths of a Kelvin. This is far colder than the current cosmic microwave background temperature of 2.725 Kelvin, which means that a solar mass black hole today absorbs more energy from the background radiation than it emits through Hawking radiation, and is therefore very slowly gaining mass rather than losing it. For a black hole to begin net evaporation under current conditions, it would need a Hawking temperature above 2.725 Kelvin, which requires a mass below approximately 0.8% of the Moon's mass. Any black hole more massive than this is currently growing, however imperceptibly, from absorption of the background radiation. As the universe expands and the cosmic microwave background temperature continues to fall, eventually the background temperature will drop below the Hawking temperature of any given black hole, and that black hole will begin to lose mass through net Hawking emission. For stellar mass black holes, this transition will not occur for an enormous time, roughly 10 to the power of 40 years after the current epoch, when the background radiation will have cooled far below the nanokelvin Hawking temperatures of these objects. After the transition, the black hole evaporates slowly, losing mass and thereby increasing its temperature according to the inverse relationship. As it loses mass, it gets hotter. As it gets hotter, it emits more radiation. The evaporation accelerates following a specific mathematical trajectory that ends in a burst of high-energy radiation as the last moments of the black hole's existence produce temperatures approaching the Planck temperature, the upper limit of what any physical theory can describe. In a final explosion that for a stellar mass black hole releases energy equivalent to roughly 1 billion nuclear weapons, but spread over an inconceivably long evaporation time. The evaporation of all black holes in the universe, a process requiring roughly 10 to the power of 100 years for the most massive, represents the final significant energy conversion process available in the post-stellar universe. After the last black hole has evaporated, what remains is only the most dilute possible distribution of photons and elementary particles in a space that has expanded to incomprehensible scale, at a temperature that approaches absolute zero asymptotically and will never quite reach it. The Hawking radiation that was emitted by these evaporating black holes will have become the universe's thermal content, cooling as the universe expands, carrying the encoded information of everything that ever fell into a black hole in some form that current theory cannot fully describe. The information paradox at the heart of Hawking radiation remains one of the deepest unsolved problems in theoretical physics. When an object falls into a black hole, all the information that describes it, the quantum states of every particle it contains, appears to be lost when the black hole eventually evaporates and the Hawking radiation it emits is perfectly thermal, carrying no information about what fell in. But quantum mechanics insists that information cannot be destroyed. The apparent contradiction between the unitarity of quantum mechanics, which preserves information, and the thermal character of Hawking radiation, which destroys it, has driven decades of theoretical work, including the holographic principle, the firewall paradox, and ongoing efforts to understand how information is encoded in Hawking radiation. The temperature of black holes, derived from a calculation that seemed complete, leads directly to a question that remains open. The cold of a black hole's Hawking emission conceals, in its perfect thermal character, a fundamental mystery about the relationship between information, gravity, and quantum mechanics. The cosmic web and the cold topology of the universe. The universe at its largest scales has a structure. It is not a uniform fog of galaxies distributed smoothly through space. It is organized into a vast, three-dimensional network called the cosmic web, a structure composed of dense clusters of galaxies at the nodes where multiple filaments meet, elongated filaments of galaxies and gas connecting those nodes, and thin sheets of galaxies at the intersections of filaments, all surrounding enormous voids, nearly empty regions of space that constitute the dominant volume of the universe and that are among the coldest and most tenuous environments in the observable cosmos. The cosmic web formed through the gravitational amplification of tiny density fluctuations that were imprinted in the distribution of matter shortly after the Big Bang. In the early universe, the distribution of matter was extremely smooth, with density variations of only roughly 1 part in 100,000. Over billions of years, gravity amplified these tiny differences. Regions that were slightly denser than average attracted more matter from surrounding regions, becoming denser still, while underdense regions lost matter to their denser neighbours and became progressively more empty. The result of this gravitational instability, sometimes called the Jeans instability, after the physicist James Jeans, who first analysed it mathematically, is the web-like structure we observe today, a cosmic architecture in which nearly all the visible mass is concentrated in a small fraction of the total volume, leaving the majority of space as cold, dark, nearly empty voids. The voids are the most extensive thermal environment in the universe. They span hundreds of millions of light years in diameter in some cases, and they collectively occupy approximately 80% of the universe's total volume. Within them, the density of matter drops to roughly 10% or less of the cosmic average. There are galaxies within voids, isolated systems that happen to form or migrate into these underdense regions. But they are rare. The dominant condition of a void is the near absence of anything that generates heat. No clusters of stars, no active galactic nuclei, no dense interstellar medium. The gas within voids, what little exists, is cooled primarily by the expansion of the universe and heated by very little else. Its temperature approaches the cosmic microwave background temperature from slightly above, warmed marginally by faint radiation from the walls of the void and by the small number of galaxies within, but fundamentally at or near the 2.725 Kelvin floor. The filaments that make up the skeleton of the cosmic web are warmer than the voids. Gas falls along filaments under gravity, converting gravitational potential energy into kinetic energy and eventually into thermal energy through shocks where the infalling gas encounters other gas and decelerates abruptly. The warm-hot intergalactic medium in filaments, sometimes called the WIM, has temperatures ranging from approximately 100,000 to 10 million Kelvin, vastly hotter than the void gas despite being far less dense than any gas in a galaxy or a galaxy cluster. The WIM contains a significant fraction of the universe's ordinary baryonic matter, the protons and neutrons and electrons that compose everything we can see or touch. Its detection has been one of the observational challenges of the last 2 decades because its diffuse character and intermediate temperature make it difficult to observe against backgrounds both hotter and colder. The clusters at the nodes of the cosmic web are the hottest large-scale environments in the universe outside of individual astrophysical objects like stars and neutron stars. Galaxy clusters contain hundreds to thousands of galaxies suspended in a vast pool of hot gas called the intra-cluster medium, with temperatures ranging from 10 million to 100 million Kelvin. This gas is detectable through its X-ray emission, since gas at these temperatures radiates primarily in the X-ray band. The intra-cluster medium is so hot that it was a cosmic puzzle for decades. What mechanism heats it to these extreme temperatures and maintains them against the efficient X-ray cooling that should cause it to cool and condense at the cluster center? The answer involves active galactic nuclei, Supermassive black holes at the centres of the brightest cluster galaxies that periodically undergo accretion events producing powerful jets that inject energy into the surrounding hot gas, preventing it from cooling and driving enormous bubbles of low-density magnetized plasma through the intra-cluster medium. The largest of these bubbles, seen as dark regions in X-ray images of galaxy clusters, contain cavities hundreds of thousands of light-years across carved by the black hole jets, and they represent some of the most energetic individual events in the current universe. The thermal structure of the cosmic web therefore spans an extraordinary range within the current universe. From the roughly 100 million Kelvin intracluster medium at the nodes, through the filament gas at millions of Kelvin, through the sparse void gas near the cosmic background temperature, to the background radiation itself at 2.725 Kelvin, and ultimately to the even colder environments produced in specific astrophysical settings described in previous chapters. This range, spanning more than 10 orders of magnitude in temperature across the large-scale structure of the universe, reflects the degree to which gravity has organized the initially smooth, post-Big Bang matter distribution into the complex, hierarchical, thermally diverse structure we observe today. Cold and the human body, what space actually does to biology. The interaction between the cold of space and biological matter is not the simple, dramatic freezing that popular culture depicts. It is governed by the same physics that governs any thermal system in a vacuum, and the result is a sequence of processes quite different from the instantaneous transformation into a frozen object that films usually portray. Understanding what space actually does to biology requires distinguishing between the direct effects of thermal cold, which are slower than most people expect, and the other properties of the space environment that cause harm on timescales of seconds to minutes rather than hours, operating entirely independently of temperature. A human body placed in the vacuum of space without protective equipment would face several simultaneous physiological challenges, of which temperature is among the least immediately lethal. The primary immediate threat is the absence of atmospheric pressure. At sea level on Earth, the atmosphere exerts approximately 101,325 pascals of pressure on every surface it contacts. This pressure keeps the gases dissolved in blood and tissues in solution, in the same way that pressure in a sealed soda bottle keeps carbon dioxide dissolved in the liquid. Remove the surrounding pressure abruptly, as occurs when a person is exposed to vacuum, and the dissolved gases come out of solution and form bubbles throughout the body tissues in a process similar to decompression sickness in scuba divers, but far more severe and instantaneous. The moisture on exposed mucous membranes, the eyes, the nasal passages, and the mouth would boil in the technical sense of transitioning from liquid to vapor at the ambient pressure of effectively zero, not because of high temperature, but because of the absence of pressure that would otherwise keep them liquid. The air in the lungs would rush out immediately if the person exhaled, or if they did not exhale, the pressure difference would cause lung damage. Loss of consciousness from oxygen deprivation would occur within approximately 15 seconds, as oxygen already in the blood was consumed without replacement. Cardiac arrest would follow within minutes. These are the mechanisms by which vacuum exposure would cause death, and they operate on timescales of seconds to minutes, entirely independent of the ambient temperature. The thermal effects, operating through radiation as the sole heat transfer mechanism, would be far slower. A human body in space, in the absence of direct sunlight, would lose heat through infrared radiation from its surface. The rate of this heat loss depends on the body's surface area, its temperature, and its emissivity, all of which can be calculated from the Stefan Boltzmann law. A typical adult human body radiating as a black body at 37 degrees Celsius would lose heat at a rate of approximately 580 watts per square metre of skin surface. For a person with a skin surface area of roughly 1.7 square metres, this represents a total radiative heat loss of about 1,000 watts. A resting human metabolism generates approximately 80 to 100 watts. The net heat loss through radiation in space for a body not receiving any solar energy is therefore roughly 900 watts, a substantial but not instantaneous drain on the body's thermal reservoir. At this rate, the body's core temperature would take many minutes to drop to levels that threaten cardiac function, and the body's periphery would cool somewhat faster than the core due to lower thermal mass and less metabolic heat generation. Death from cold alone, in the absence of the other effects described above, would require something on the order of 30 minutes to several hours, depending on body composition and the specific thermal environment. In direct sunlight, the calculation changes dramatically. The solar flux in Earth orbit is approximately 1,361 watts per square metre. A human body presenting roughly 0.5 square metres of cross-sectional area to direct sunlight in the skin absorbs roughly 680 watts of solar radiation. Subtracting the body's own radiation loss and adding the metabolic heat generation, a body in direct sunlight would actually accumulate heat and risk overheating rather than freezing. The danger in direct sunlight without protection would be hypothermia and severe ultraviolet radiation damage to the skin and eyes, not hypothermia. This counterintuitive result reflects the basic physics of thermal radiation. In the absence of any convective or conductive medium, the direction and intensity of radiation matter enormously for the net thermal balance. The temperature limits of the human body as a biological system are determined by the chemistry of life, rather than by the physics of heat transfer. The enzymes that catalyze biochemical reactions in cells have operational temperature ranges determined by their molecular structure. Below approximately 35 degrees Celsius in the body core, enzymatic reactions slow enough to impair cardiac function and brain activity. Below approximately 30 degrees Celsius core temperature, cardiac arrhythmias become likely, and below approximately 25 degrees Celsius, the heart may stop. Above approximately 42 degrees Celsius, proteins begin to denature irreversibly, enzymes lose their catalytic function, and cell death accelerates. The window of temperatures compatible with the continued function of human biology is roughly 25 to 42 degrees Celsius in the body core, a span of 17 degrees Celsius within which all the complexity of human physiology can operate. Against the temperature range of the universe, from billions of degrees in neutron star mergers to the 2.725 Kelvin of the cosmic background, this 17-degree window is an infinitely narrow sliver, and maintaining it in an environment that imposes 2.725 Kelvin as the default requires continuous active thermogenesis from metabolism and highly effective thermal insulation from clothing or spacecraft systems. The fact that a human body does not instantly freeze in space reveals an important distinction between temperature and heat. Temperature measures the average energy of particles within a substance. Heat is the transfer of that energy from one place to another. Space is extraordinarily cold in the sense that it contains very little thermal energy, but it is also extraordinarily empty. Because there are almost no particles available to carry energy away through conduction or convection, the body can lose heat only through radiation, which is a comparatively slow process. The popular image of an astronaut flash freezing upon exposure to vacuum reflects an intuitive misunderstanding based on everyday experience, where cold air, cold water, or cold surfaces rapidly draw heat from the body through direct contact. In space, there is no such contact. This distinction becomes even more important when considering the preservation of biological tissue over long periods. A body exposed to vacuum in deep space would gradually cool, dehydrate and freeze as water sublimated directly from ice into vapor. The process resembles freeze-drying more than ordinary freezing. Over months and years, the tissues would become increasingly desiccated, with much of the body's water content slowly escaping into the vacuum. The resulting remains would be brittle and chemically altered, but not necessarily destroyed. In some respects, the vacuum of space acts as a remarkably effective preservation environment because it eliminates oxygen, moisture, and microorganisms, the primary agents responsible for decomposition on Earth. However, preservation is not permanence. Over longer timescales, the same cosmic radiation environment that fills interplanetary and interstellar space would gradually break down biological molecules. High-energy cosmic rays and solar energetic particles penetrate tissue, sever chemical bonds, and damage complex organic structures. DNA, proteins, and cell membranes would accumulate radiation damage continuously. Over centuries and millennia, the molecular architecture that once supported life would be progressively erased, even if the larger physical structure remained recognizable. This interaction between biology and the thermal environment of space highlights a broader truth about life in the universe. Living organisms do not merely require energy. They require a narrow range of conditions in which energy flows can be controlled. Too much heat and biological molecules fall apart. Too little heat and the chemistry of life slows toward inactivity. Life exists in a delicate thermodynamic balance between these extremes. The universe, by contrast, is dominated by environments that lie far outside that balance. Most of cosmic space is either vastly colder than life can tolerate or vastly hotter than any biological structure can survive. The continued existence of life on Earth is therefore not a consequence of typical cosmic conditions, but of an extraordinarily rare thermal equilibrium maintained by a planet orbiting at just the right distance from a stable star. Cold as a tool: how astronomers use temperature to see the universe. The cold of space is not merely a challenge to be survived by spacecraft and avoided by human beings. It is also a scientific resource, a property of the cosmic environment that enables specific kinds of astronomical observation that would be impossible in a warmer setting. The most sensitive detectors in modern astronomy must be operated at temperatures approaching the cosmic background or colder, and the scientific discoveries that these instruments have made, from mapping the cosmic microwave background in precise detail to detecting the infrared emission of the earliest galaxies to characterizing the atmospheric composition of exoplanets, all depend fundamentally on the ability to cool detectors to temperatures where their own thermal noise falls below the signal they are trying to detect. The fundamental reason detector cooling is required connects to the physics of thermal radiation described throughout this script. Any object warmer than absolute zero emits electromagnetic radiation. At room temperature, approximately 300 Kelvin, the peak emission is in the mid-infrared, around 10 micron wavelength. An infrared detector operating at room temperature is therefore constantly flooded with photons emitted by its own housing, the surrounding electronics, the telescope structure, and the atmosphere if the telescope is on the ground. This thermal background from the instrument itself is many orders of magnitude brighter than the faint astronomical signals the detector is trying to measure. The only way to reduce this self-generated thermal noise is to cool the detector to temperatures where its own emission becomes negligible relative to the astronomical signal. For near-infrared observations, cooling to roughly 70 Kelvin using liquid nitrogen is often sufficient. For mid-infrared observations, temperatures of 10 to 20 Kelvin are needed. For submillimeter and microwave observations, temperatures of a few Kelvin or below are required, achieved using liquid helium cooling or mechanical coolers. The James Webb Space Telescope's mid-infrared instrument operates at temperatures below 7 Kelvin specifically to reduce its own thermal emission to levels where the faint infrared signals from the most distant galaxies in the universe, light that has been traveling for more than 13 billion years and has been redshifted into the mid-infrared by the expansion of the universe, can be detected above the noise floor. The telescope's elaborate sun shield, cooling its optics and instruments to approximately 40 Kelvin passively, reduces the thermal background from the telescope structure itself by orders of magnitude compared to what a room temperature telescope would produce. Without this cold, the faintest signals from the earliest universe would be completely hidden beneath the thermal glow of the telescope's own mirrors and housing. The cold of the cosmic environment, achieved through careful thermal design, exploiting the Sun-Earth-Moon geometry at L2, is what makes the telescope's deepest observations possible. The South Pole Telescope in Antarctica exploits the natural cold of Earth's southern polar region to achieve similar advantages for microwave astronomy. Water vapor in the atmosphere absorbs microwave radiation before it reaches telescopes on the ground, creating an atmospheric noise floor that limits the sensitivity of cosmic microwave background measurements. The Antarctic atmosphere contains far less water vapor than the atmosphere at any lower latitude site, because the extreme cold has frozen out most of the moisture that would otherwise be present. At the South Pole, where temperatures regularly fall below -60°C, the atmosphere is unusually dry and therefore unusually transparent to the microwave wavelengths of the cosmic background. This natural cold makes Antarctica one of the best sites on Earth for observing the oldest light in the universe, and the observations made from the South Pole Telescope and its predecessors have provided some of the most precise measurements of the cosmic microwave background's temperature fluctuations, enabling detailed tests of cosmological models and measurements of fundamental parameters describing the composition and geometry of the universe. Cryogenic bolometers used in submillimeter and microwave detectors must be cooled to temperatures below 1 Kelvin to achieve the sensitivity needed for the faintest astronomical measurements. These devices measure the tiny temperature rise produced when a photon is absorbed by a thermally isolated absorber, converting the photon's energy into a measurable electrical signal. At temperatures below 100 millikelvins, the thermal noise in the bolometer drops low enough that individual photons can be detected with near unity efficiency. Achieving these temperatures in a space environment requires multi-stage cooling systems that successively cool the detector through liquid helium temperatures, then through adiabatic demagnetization refrigerators or dilution refrigerators that can reach the millikelvin regime. The Planck satellite, launched in 2009 to map the cosmic microwave background, carried detectors cooled to 100 millikelvins in space, making it the coldest known object ever placed in orbit. The data it returned produced the most precise all-sky map of the cosmic microwave background ever made, revealing temperature fluctuations of 1 part in 100,000 across the sky that encode information about the density variations in the universe just 380,000 years after the Big Bang. Ironically, the coldest satellite ever built was used to study the coldest light in the universe, the thermal afterglow of the Big Bang that fills all of space at 2.725 Kelvin. The relationship between cold and astronomy extends beyond detectors themselves to the physical environments being studied. Some of the most important structures in the universe can only exist because they are cold. Giant molecular clouds, the birthplaces of stars and planetary systems, maintain temperatures typically between 10 and 20 Kelvin. At these temperatures, thermal motions within the gas are slow enough that gravity can begin to overcome internal pressure, allowing regions of the cloud to collapse and form new stars. If these clouds were substantially warmer, thermal pressure would prevent collapse and star formation would become dramatically less efficient. In a very real sense, every star in the galaxy, including the Sun, owes its existence to the ability of matter to cool. The same principle applies on smaller scales throughout planetary system formation. The protoplanetary disks surrounding young stars contain regions where temperatures fall low enough for volatile compounds to condense into solid grains. Water freezes beyond the so-called snow line. Farther out, carbon dioxide, methane, and ammonia freeze as well. These frozen materials contribute enormous amounts of solid mass to the disk, enabling the rapid growth of planetesimals and eventually giant planets. Jupiter, Saturn, Uranus, and Neptune formed in regions where temperatures were sufficiently low for abundant ices to exist. The architecture of our solar system, including the distinction between rocky inner planets and gas-rich outer planets, is fundamentally a consequence of temperature gradients established billions of years ago in a cooling disk of gas and dust. Cold environments also preserve information that would otherwise be erased. Comets spend most of their existence in the Kuiper Belt and Oort cloud, where temperatures are typically below 50 Kelvin, because chemical reactions proceed extremely slowly at these temperatures. Cometary nuclei remain relatively unchanged from the era of solar system formation. When spacecraft analyze the composition of cometary ice and dust, they are effectively examining material that has been stored in a deep freeze for 4.6 billion years. Missions such as Rosetta revealed that comets contain complex organic molecules, isotopic signatures, and primitive materials that provide direct clues about the conditions under which the solar system formed. At even lower temperatures, quantum mechanical phenomena begin to dominate the behavior of matter. Laboratory experiments on Earth routinely cool atoms to microkelvin and nanokelvin temperatures, billionths of a degree above absolute zero. At these temperatures, particles cease behaving as distinct individual objects and instead occupy collective quantum states that can extend across an entire experimental apparatus. Bose-Einstein condensates, first created in 1995, represent a form of matter that exists only because thermal motion has been almost completely eliminated. The ability to study matter in these regimes has transformed fields ranging from atomic physics to precision measurement and quantum computing. The scientific value of cold therefore extends far beyond comfort or survival. Cold is not merely the absence of heat. It is a physical condition that enables the formation of stars, preserves the history of planetary systems, allows the detection of the faintest signals from the distant universe, and reveals forms of matter that cannot exist under ordinary conditions. The universe's immense coldness, which might initially appear hostile or empty, is in fact one of the fundamental reasons complex structures exist at all. Without cold, there would be no stars forming from molecular clouds, no planets condensing from protoplanetary disks, no precise measurements of the cosmic microwave background, and ultimately no observers capable of asking why the universe is cold in the first place. The future cold of the universe, a timeline of cooling. The universe has been cooling since its first moment, and it will continue cooling for longer than the current age of the universe multiplied by any number that can be meaningfully written in standard notation. Tracing this cooling trajectory forward from the present provides a specific, physically grounded account of what the universe will become over timescales that dwarf the entire history of life on Earth, and it frames the present moment, already 13.8 billion years into cosmic history, as an extraordinarily early and thermally rich phase in a story that has barely begun. The most immediate phase of future cooling on an astronomical timescale is the continuation of the current epoch of star formation. Stars are forming right now throughout the Milky Way and in galaxies across the observable universe, converting cold molecular cloud gas into hot plasma through the process of gravitational collapse and nuclear ignition. This star formation will continue for billions of years, but at a rate that is declining as the available reservoir of cold gas suitable for star formation is gradually consumed. Current estimates suggest that the peak of star formation in the universe occurred approximately 10 billion years ago, when the rate at which new stars were being born across the universe was roughly 10 times higher than it is today. Since that peak, the rate has been declining, and it will continue to decline over the next tens of billions of years as the molecular cloud gas in galaxies is progressively converted into stars, locked up in stellar remnants, or heated to temperatures where it cannot cool efficiently enough to collapse and form new stars. The Sun has approximately 5 billion years of hydrogen-burning main sequence life remaining. After that, It will expand into a red giant as the exhausted hydrogen core contracts and shells of hydrogen outside the core ignite, swallowing the inner planets and converting Earth, if it survives as a separate body, into a scorched, airless rock. The Sun will then shed its outer envelope as a planetary nebula, leaving behind a white dwarf, a hot, dense stellar remnant approximately the size of Earth, glowing with the residual heat of its formation and its nuclear past. White dwarfs cool progressively through radiation over trillions of years. The oldest white dwarfs in the galaxy are already approximately 13 billion years old and have cooled to temperatures below 4,000 Kelvin, dim and orange, rather than the brilliant white they would have been when newly formed. Given enough time, white dwarfs cool to temperatures below 1,000 Kelvin, becoming black dwarfs, objects too cool to emit visible light, detectable only in the infrared and radio. On timescales of hundreds of billions to trillions of years, the galaxy's population of white dwarfs will transition progressively into a population of cold, dark, cooling objects, and the galaxy will become darker and cooler. The last stellar light is expected to fade approximately 100 trillion years from now, when the final red dwarfs, the most fuel-efficient stars, burning hydrogen so slowly they have main sequence lifetimes of trillions of years, finally exhaust their fuel and collapse into dim stellar remnants. After this point, a dark era begins. No more stars, no more nuclear fusion. The energy sources that have powered the universe's luminous structure since the first stars ignited are gone. What remains is a population of stellar remnants, white dwarfs, neutron stars, black holes, and brown dwarfs that never ignited nuclear burning, slowly cooling and darkening in a universe that continues to expand and in which the cosmic background temperature continues to fall. Over the following timescales, measured in 10 to the power of 20 to 10 to the power of 40 years, even the cold stellar remnants will experience further change. The quantum mechanical process of proton decay, predicted by various grand unified theories of particle physics, though not yet experimentally confirmed, would dissolve the atomic nuclei in white dwarfs and neutron stars over timescales of perhaps 10 to the power of 34 years, converting them progressively into black holes and eventually into elementary particles. Black hole collisions and mergers will reduce the population of black holes to fewer larger objects over timescales of 10 to the power of 20 to 10 to the power of 30 years through gravitational radiation, the same process of energy loss through gravitational waves that the LIGO detector has been observing in the mergers of stellar remnants. The universe during this dark era will be cold, dark, and increasingly dominated by the mass energy of black holes, surrounded by an ever-cooling sea of background radiation. The final phase of the universe's accessible thermal history is dominated by the evaporation of black holes through Hawking radiation on timescales up to 10 to the power of 100 years, as described in Chapter 13. As the last black holes evaporate, they convert their mass into Hawking radiation, the final significant addition of energy to the universe's thermal content. This radiation, itself cooling as the universe continues to expand, joins the residual photons and sparse elementary particles that constitute the universe's remaining content. The temperature at this epoch is unimaginably low, a number so close to absolute zero that the gap between the two is smaller than any temperature ever measured by any instrument. The universe approaches its final cold not in a single moment, but asymptotically, always falling, never quite reaching the floor, governed by the same thermodynamic principles that apply to every cooling system in physics. What the cold of space tells us about our place in the universe. The temperature of the universe, traced from the 10 to the power of 32 Kelvin Planck temperature at the first moment after the Big Bang to the 2.725 Kelvin cosmic background today, and projected forward to the near-zero temperature of the deep future, tells a story that extends far beyond physics. It is a story about where we are in the universe's history. what our existence means in the context of that history, and why the specific thermal conditions of the present epoch are not merely a backdrop to human existence, but a necessary prerequisite for it. Life as it exists on Earth, and as it is likely to exist anywhere in the universe based on the chemistry we know, requires thermal gradients. Not the absence of cold, but the presence of both warm and cold simultaneously, with warm and cold connected by some pathway that allows energy to flow from one to the other. On Earth, that gradient is provided by the Sun. Its surface at 5,500 degrees Celsius is the warm source, and the deep cold of space at 2.725 Kelvin is the cold sink. The energy that drives every biological process on Earth, every chemical reaction in every cell, every heartbeat, every photon captured by photosynthesis, ultimately flows along this gradient from the Sun's heat to the cosmic cold. Photosynthesis captures a small fraction of the solar energy that falls on Earth and converts it into chemical energy stored in organic molecules. That energy is then released through metabolism and used to do the work of building and maintaining biological structures, ultimately being released as heat that radiates into the cold of space. Life is, in thermodynamic terms, a process that extracts useful work from the temperature gradient between the Sun and the universe. If the universe were uniformly warm, with no cold sink for energy to flow into, there would be no gradients and no possibility of any process doing useful work, including the processes of life. If the universe were uniformly cold at its current background temperature, with no warm sources, there would equally be no gradients and no life. It is the specific combination of warm stars embedded in a cold cosmic background that makes the energy gradient available on which life depends. The cold of space is not merely the environment in which life exists, it is a thermodynamic partner to the warmth of stars, the necessary other half of the gradient that makes life possible. This perspective reframes the common intuition that cold is the enemy of life. Cold is not the enemy of life. The absolute uniformity of temperature is the enemy of life, whether that uniformity is at high temperature or low. The cold of the cosmic background, combined with the warmth of nearby stars, is actually part of what makes life possible. Remove the cold, equalize the temperature of stars and background, and the gradient vanishes along with any possibility of biological complexity. The universe's coldness is, in a very precise physical sense, part of why we exist. The present epoch of cosmic history is uniquely suited to life in ways that will not persist indefinitely. As the universe ages, stars will exhaust their fuel. The temperature gradients available for biology will diminish as each star dies. In the far future, the universe will be cold and dark, with no warm sources to provide the gradients on which any process we would recognize as life depends. The window of cosmic time during which the universe is thermally structured in a way compatible with life, with warm stars embedded in a cold cosmic background, is finite, and we happen to exist within it. This is not necessarily a coincidence in the superficial sense. Any civilization capable of observing the universe will exist during a period when warm stars still shine, because that is a prerequisite for the chemistry of life. But it is worth recognizing that the 13.8 billion years of cosmic history that have passed represent only the very beginning of the universe's total timeline, and that the thermal richness that makes life possible is a temporary condition in a universe that is trending, irreversibly and in the very long run, toward the cold silence of maximum entropy. Understanding the cold of space is therefore understanding something fundamental about both the physics of the universe and our place within it. The 2.725 Kelvin of the cosmic background is not an arbitrary number or a minor detail of the universe's properties. It is a direct consequence of the Big Bang, of the expansion of the universe over 13.8 billion years, and of the specific physics that governs how electromagnetic radiation interacts with the expanding geometry of space-time. It is the temperature of the oldest light in the universe, the last remnant of the fireball from which everything emerged. It is the thermal baseline against which every warm thing, every star, every planet, every organism represents a temporary departure. And it is falling, slowly and continuously, as the universe moves toward its final cold equilibrium. The future cooling of the universe is not speculation in the casual sense. It follows directly from observations that have already been made and from physical laws that have been tested to extraordinary precision. The expansion of the universe causes the wavelength of every freely travelling photon to stretch over time. As wavelength increases, energy decreases, and because temperature is related to the average energy of radiation, the temperature of the cosmic background falls. When the universe was half its current size, the cosmic microwave background temperature was approximately 5.45 Kelvin. When it was 1/10 its current size, the temperature was approximately 27 Kelvin. Looking backward through cosmic history is therefore equivalent to looking toward a hotter universe, while looking forward means looking toward a colder one. In approximately 100 billion years, the expansion of the universe will have carried nearly all galaxies beyond the observable horizon of any civilization that might then exist within the Milky Way's future merger remnant. The cosmic microwave background will have cooled to a tiny fraction of its present temperature and stretched to wavelengths so long that detecting it will become extraordinarily difficult. Future astronomers may find themselves in a universe where the evidence for the Big Bang has largely disappeared beyond observational reach. The stars of their local galaxy will still shine, but the broader cosmic context that allows us to reconstruct the universe's history today may no longer be accessible. On even longer timescales, the thermal evolution of the universe becomes increasingly dominated by stellar death. Star formation is already declining compared to its peak roughly 10 billion years ago. Galaxies are gradually consuming the cold gas reservoirs from which new stars form. Every generation of stars converts hydrogen into heavier elements and disperses some of that material back into space. But the total supply of star-forming gas decreases with time. Eventually, star formation will effectively cease. The universe will enter what astronomers call the degenerate era, a period dominated not by luminous stars, but by stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs provide a particularly striking example of cosmic cooling. These objects are the exposed cores of stars like the Sun, initially possessing temperatures of tens of thousands of degrees. They contain no internal energy source and simply radiate their stored heat into space. Over trillions of years, they cool steadily, becoming redder, dimmer, and eventually invisible. Theoretical calculations predict that after sufficiently long times, they will become black dwarfs, cold stellar corpses whose temperatures approach that of the surrounding universe. No black dwarf currently exists because the universe is not yet old enough for any white dwarf to have cooled that far. The same process applies on larger scales. Neutron stars gradually cool, planets cool, brown dwarfs cool. Every isolated object in the universe radiates energy away and moves incrementally toward thermal equilibrium with its surroundings. The direction is always the same. Heat flows from hotter objects to colder ones, never the reverse without external work being performed. The entire thermal history of the cosmos can therefore be viewed as a vast redistribution of energy from concentrated forms toward increasingly diffuse ones. This trend is captured by the concept of entropy. In thermodynamics, entropy measures the number of microscopic configurations compatible with a system's macroscopic state. High entropy states are more probable because they can be realized in more ways. A hot star surrounded by cold space represents a relatively low entropy configuration because energy is concentrated in one location. A universe where that energy has been dispersed uniformly is a higher entropy configuration. The second law of thermodynamics states that entropy tends to increase, and the cooling history of the universe is one manifestation of that principle on the largest possible scale. The ultimate consequence is a scenario often called heat death. Despite the name, heat death is not a state of excessive heat. It is a state in which temperature differences have effectively vanished. Energy still exists, but it is distributed so uniformly that no useful work can be extracted from it. Stars no longer shine. No significant chemical reactions occur. No engines can run. No biological metabolism can function. The universe becomes thermodynamically exhausted, not because energy has disappeared, but because it is no longer organized into gradients that can power complexity. This perspective reveals something profound about the present moment in cosmic history. We inhabit a universe that is neither too hot nor too cold, neither too young nor too old. The first few 100,000 years after the Big Bang were too hot for atoms to exist. The far future will be too cold and too uniform for complex structures to persist. Between these extremes lies a relatively brief era in which galaxies, stars, planets, chemistry, and life are possible. The existence of observers is tied directly to this thermal window. Every living thing, every ecosystem, every civilization, and every scientific instrument operates by exploiting temperature differences that ultimately trace back to the universe's thermal history. The warmth of Earth's surface, the energy of sunlight, the chemical gradients that sustain biology, and the cold darkness of interstellar space are all connected components of the same thermodynamic story. The cold of the universe is not merely an environmental condition. It is one half of the temperature difference that powers every complex process we know. In that sense, the 2.725 Kelvin background temperature is more than a measurement. It is a reminder that the universe is still cooling, still evolving, and still carrying forward the consequences of events that occurred 13.8 billion years ago. Every warm object in existence today, from stars to human bodies, shines against that cold backdrop as a temporary concentration of energy. The contrast between those islands of warmth and the immense cold surrounding them is what makes complexity possible. And it is that contrast, not warmth alone, that defines the era of the universe in which we happen to live. The cosmological future of temperature and entropy. The coldest temperature in the natural universe, 1 Kelvin in the Boomerang Nebula, sits 1 degree above the theoretical floor. The average temperature of the universe sits 2.725 degrees above it. Every warm thing, every burning star, every heated planet, every living cell represents an exception maintained against the background of that overwhelming cold by whatever local process provides the energy to sustain it. We live on one of those exceptions, a planet warmed by a star in the coldest large-scale environment the universe has produced since the Big Bang. The cold of space is not merely the temperature of the places we have not reached, it is the condition to which everything trends. Stars cool to white dwarfs, which cool to black dwarfs. Galaxies exhaust their gas and grow dark. Black holes evaporate through Hawking radiation, and their energy disperses into space as photons that cool as the universe expands. The second law of thermodynamics is the most reliably obeyed law in the history of physics, and it permits no exceptions on a long enough timescale. Entropy increases. Temperature gradients flatten. The universe cools toward its final equilibrium. What makes this story not depressing but clarifying is that the cold tells us where we are. We exist in the brief window between the Big Bang's fire and the universe's final cold, in the epoch when stars still burn and gradients still drive complexity. We are not separate from the cold of space, regarding it from a safe distance. We are embedded in it, temporarily warm, temporarily complex, temporarily aware of the cold that surrounds us, because the particular accident of a star and a planet placed us here at this specific moment in the universe's cooling history. The cold has always been there, patient and absolute. 2.725 Kelvin in every cubic centimetre of space, and it will be there long after the last star has cooled and the last black hole has evaporated. The cold is the universe's default. Everything warm, including us, is the deviation.